In this video, we're going to discuss the variation of the atomic radius as you go across the periodic table. We know from experiments that the atomic radius, which is a measure of the size of an atom, changes in this fashion. As you go down the periodic table, the atomic radius increases, and then the atomic radius also increases as you go from the right to the left. Okay? So we're going to try to explain those two trends. The first one is fairly easy to understand. If we actually take the alkali metals, right, the electronic configurations are going to be as follows. Lithium is going to be 1s2, 2s1, and then the next one over is going to be sodium. It's going to be the prior rare gas, and then 3s1, and then so forth, right? So you go to potassium, and the last electron will be 4s1, and then you go to rubidium, the last electron will be 5s1, and so forth. Right, so you can see that as we go down the periodic table, what happens is that electrons start populating orbitals or wave functions that have an increasing principal quantum number, n. And what we actually know is that the principal quantum number n dictates the extension of the wave function, okay, the extension of the orbital, and orbitals with larger principal quantum number have a much further extension than those with a smaller one. Okay, so we can see how the atomic radius is connected to the size of the orbital that the last electron occupies. Okay, so that is relatively easy to understand. Something that is not so easy to understand is to figure out why the atomic radius increases as we go right-left, or why it decreases as we go from left to right. Okay, and to illustrate that, we're actually going to be using two pretty common elements, which are going to be carbon and nitrogen, again in an attempt to address why the unique radius changes the way that it does. Okay? All right, so let's think about carbon and nitrogen. Okay, the electronic configurations are 1s2, 2s2, 2p2, and then for nitrogen you will have 1s2, 2s2, 2p3. Right, so the only change in the electronic structure is that you have one more electron in nitrogen than you do in carbon. And what we know is that the size of an atom of nitrogen, okay, is a little bit smaller than the size of an atom of carbon, even though it actually has more electrons. Well, the reason for this trend is has to be sought in a balance between something that we call the effective nuclear charge, okay, the number of protons that you actually have in the nucleus, and the electronic repulsion. Okay, so let's think about the nuclear charge first. Notice that carbon has 6 protons. And the 6 protons attract the 6 electrons in some manner. And then we have that nitrogen has one more electron, but it also has one more proton, and then you have 7 protons. Okay, so again, there's two things that can repeat here. Electrons tend to repel each other, okay, and that would mean that the atom would grow larger if you have more electrons. At the same time, when you grow the number of protons, those electrons can be attracted by a larger nuclear charge, okay, which tend to make the extension of that atom a little bit smaller. Okay, so which one wins out depends a little bit on the balance of those two effects, which is the electronic repulsion and then the nuclear charge. Okay, so let's then take a look at in a little bit more detail at the details of the electronic structure of carbon and nitrogen. Okay, when we actually think about these p orbitals, the way that this would work is as follows. You would have for carbon 6 positive charges, you will have the 1s electrons, and you have the 2s electrons, and I'm just going to draw here the 2p orbitals. Right, so that will be the nucleus, and then the 2p orbitals will be something like this. You will have this one, which we're going to call the 2px, then that one, which we're going to call the 2py, and then coming in and out of the plane, you will have the third 2p orbital, which is going to be difficult to draw in 2 dimensions, but I'm just going to draw it here at an angle. Okay, and again, this means that this orbital is coming in and out of the plane. Alright, so the electronic occupation would be 1 electron in the 2px, and then 1 electron in any of the other ones. Arbitrarily, I'm going to assign it to the 2py. They must have parallel spins according to Hund's rule. Okay, so then when we go to nitrogen, you now have 7 protons in the nucleus. Okay, and then you have here your 2px, your 2py, and then your 2pc coming in another plane, which I'm going to draw here at an angle. Okay, so that is the 2px, that is the 2py, and this is the 2pc. All right, and there's one electron in each one of the orbitals. All right, so the idea is that, again, the balance of the electron repulsion and the nuclear charge is going to dictate the size of the atom. Right, so the idea is that when you go from carbon to nitrogen, you actually have one more electron that in principle should increase the repulsion between those electrons, and then that will lead to a larger orbital. However, to a larger atom. However, what you actually have is that there's an increase in nuclear charge as well, and that would tend to decrease the size of those of that atom. The question is, which one of these two factors wins out? The increase in the nuclear charge as you go from carbon to nitrogen, or the increase in the electronic repulsion because you have more than one electron. Well, it turns out that is the increase in the nuclear charge that is more important than the increase in the electronic repulsion, because if you notice the electronic configuration, the new electron as you go from carbon to nitrogen is placed in an orbital which is actually perpendicular to the other two. Right? This electron is in a region of space which is rather different from the 2px and 2py, and if that's the case, then the electronic repulsion is not very big, okay? Because the electronic repulsion is not very big, but the nuclear charge is actually increasing by one full charge. What we can say is that the effective nuclear charge felt per electron in this atom is actually larger in nitrogen than it is in carbon, okay? So that is what explains that this atom is actually smaller than that one, and the atomic radius increases from right to left in the periodic table. Again, the idea is that as you move from the left to the right, you're increasing the number of electrons, but you're increasing the number of protons as well. And because electrons tend to be placed in perpendicular orbitals, okay, which don't repel each other very effectively, okay, the increase in the nuclear charge is more important, and that ends up contracting the atoms as you go from the left to the right. Okay, so in this video we have seen how the atomic radius changes across the periodic table. We have seen how it increases as you go down in a group, and we also have discussed why the atomic radius increases as you go from the right to the left.